Remember insertion sort? This is where we left off last time, right? And if I was standing on a subway describing insertion sort, what would I say? I would say, well, what I'm going to do is I'm going to maintain a subset of the elements that are sorted within a list, right? So a subset of the numbers are already over here. What have I just done? I've described the loop invariant, right? Right? The remaining elements are off to the side somewhere. Oh, that's part of the loop invariant, right? Initially, think of the first element in the array as being a sorted list of length 1. What did I do? I just established the loop invariant, right? And now we're going to maintain the loop invariant. One at a time, we take an element that's off to the side and we sort it where it goes, right? I've maintained the loop invariant while making progress, right? Insert it where it belongs. This gives a sorted list that's one element longer. Gives a sorted list. I've maintained the loop invariant of one longer. I've made progress, right? When the last element has been inserted, exit condition. The array is completely sorted, right? Everybody see that? Can you imagine saying that on the subway? All right. All right, so you guys might not be up for running time yet, but the running time is n squared. And why is it n squared? Is because when I take the 62, I have to put it where it goes, right? And how long does that take for me to find out where it goes? It takes the length of the little guy, right? So when it's of length 1, it takes me time 1. It's of length 2, it takes me length 2. So the time is 1 plus 2 plus 3, right? And then what does that add up to? It adds up to n times n plus 1 over 2, right? I'm going fast here because you did this in 1019, and we will do it in 3101, and we're not doing it now, right? Order n squared, right? All right, so now ready for binary search? These are the things we're supposed to cover, all right? So binary search, the precondition is I have a list that's sorted and a key that I'm looking for, right? And what are you supposed to do? If it's in there, you're supposed to find it. If it's not in there, you're supposed to say it's not in there. If it's in there 5 times, you can return any of them, right? Everybody got the problem? So we need a loop invariant, right? Don't worry about it. We'll do it next class. All right? So remember loop invariant. And outside, and let me tell you what those slides say. Outside, people are like, what's a loop invariant? And I said, well, it's the statement that you're doing fine so far, right? You're still on the path, right? Well, what does that mean? Well, different algorithms, you would be fine different ways. The definition of fine, we're doing fine so far. Yeah. You know, your statements, they often talk like you're telling me something, not like you're asking me something. Let me finish what I'm saying. All right. So I want lots of questions, but not discussions. All right. So where was I? So what is a loop invariant? It says, it kind of tells you the types of places you want to go between here and where you're going, right? What does it mean that we're fine so far, right? Well, here, what find so far means is that I'm looking for something, and after I've worked for a while, I've narrowed the search space, right? And if the search space is smaller, then what do we want to say about it? Well, you could say what you're looking for is in there, but it might not be anywhere, right? We could say it's not outside, but maybe there are two of them. There could be one inside, one outside. That's okay. What we want to say is if it's anywhere, then at least one of them's inside. Right? Does that make sense? That you haven't gone wrong. It's our definition of you haven't gone wrong. Right? So that's our loop invariant. Everybody good? All right. So if the key is contained in the original list, then the key is contained in the sublist. Right? Everybody good? All right. What's our step? Remember, we're supposed to make progress. Well, that means we're supposed to make our list smaller, right? Because the smaller it is, the more we're closer to finding it. And we need to maintain our loop invariant. So what we do is we cut the list in half. We like brutality, right? And we compare it to the middle guy. And if what we're looking for is smaller than this middle guy, then we keep the left half, right? And if what we're looking for is bigger than the middle half, then we keep the right half, right? Everybody good with that? Just so happens it's not, yeah, let's not get into that. How much progress do we do? The list comes down by a factor of 2, right? So one thing you should have learned in 1019 is if you take the number n and you divide it by 2 and you divide it by 2 and you divide it by 2, how many times you divide it by 2 until you get to 1? Log n time, right? So this is log n. Right? How do you establish the loop invariant? You start with the entire list, right? How do you stop? Well, if your list is of size 1, you look at it, right? One thing I skipped there is we never actually said, is it the key? We just went left or right, right? So now when it's down to one thing, you actually look and say, is this my key? And if it's your key, you found it, right? And if it's not your key, it wasn't there, right? Because if it was there, it would be here, but it's not here, so it's not there, right? And that, running time log n. That's it. Any questions about it? How are we doing for time? We're doing okay? We now have 7 minutes. See how I did math? I'm like a math doer. Everybody good? Any questions about this? Are we going too fast? Are we losing people? We're not losing him. We're losing you guys. All right. There's the code. Should we go through the code, or you gotta? I don't like code. So in 10.9 and 3101, we go through all different subtle ways in which you could get this code wrong. Evidently, there was a study when I was first in '82. I was at Waterloo. That's when it started. And what was everybody doing in computers? They were sorting, right? It was before the day of large language models. And so they cared about sorting, and they asked expert coders to code it up, and 80% of them wrote code that didn't work, right? So my PhD advisor, when she teaches this course, does horrific, long, formal proofs that this works, right? And do we want to do that? No, right? We don't, right? But we still want code that works. So I think what I'm doing is sort of a balance, right? You make sure you maintain, right? So what are the morals here, right? Make sure you have a well-defined loop invariant. Make sure that you establish it. Make sure that you maintain it while making progress. Make sure that from the exit condition and the measure and the loop invariant, you get the post condition, right? We do them very casually like this. We don't have to be 1090 formal, right? All right, ready for more? All right, so now oh, this is interesting. This is actually one of the things we're really supposed to cover in this course, all right? So I whipped this up in 3101 because I assume you've seen it already. But where do you see it? You see it today, all right? So let's think about, oh, well, we're not doing insertion sort yet, but let's for a moment think about insertion sort, right? I'm inserting this guy, right? Now, how do I can use binary search to find out where it goes, right? But then I got to shift everybody over, right? And that's nasty. So instead, maybe we'll use the linked list, right? But then you can't do binary search, right? So how do you balance sorted list with binary search? This, all right? This is a data structure that lets you do binary search and lets you play with pointers, all right? And it's called a binary search tree. Why? Because what do you do in it? You do binary search, right? And what is it? It's a binary tree. In this case, it's fully balanced. But as you insert things and delete things, it might not be fully balanced, which is no good. And so then we'll teach how to rebalance it, right? But that's for a later day. So right now, we just have this binary tree. Each node has one of your key objects. And we have, right? So remember I told you I'm really big about loop invariants. But you can kind of go out about your data structure, right? We're adding things, we're deleting things. You could call that a loop where we have a loop invariant, or you could call it a data structure invariant, right? So what's our data structure invariant is that if you look at any node, right? Any node in the tree, it has a value. Everybody in its left subtree smaller or equal, right? Everybody in its right subtree is bigger or equal to it, right? Can everybody kind of eyeball and see what that's happening, right? Why do I let it be equal? It's because suppose every number was 38. Then I want to still be able to balance it, right? Everybody good with that? All right. Now we have this data structure, and we're going to do binary search. What's our loop? What we're going to do is we're going to start at the top. And when our loop invariant is that we have a sub narrowed search space. And how are we going to get our narrowed search space is we're going to have our finger on one of these nodes, right? If you have a finger on one of these nodes, let's see what we do it here. There, I got my finger on the 25. What it means is, right, I'm looking for 17. So if 17 is anywhere, it's in the subtree underneath where my finger is. Remember, fingers are positions that we talked about how to deal with, right? So there I am. I got my finger on 25. My loop invariant is that if it's anywhere, it's in there. So what do? I'm sitting at the 25. What do? I compare it to the 25, right? I compare it to the 25. And this time we're going to have to say if it's equal, right? Here with 3 cases, right? Do we have cases? Right, so if it's smaller, you just move your finger to the 17. If it's equal, you go home. If it's bigger, you move your finger to the 31, right? And if you're at a 4, you do the same, right? But if you drop off into the empty tree, then you say it's not there, right? Everybody follow that? Everybody good? What's the running time? I'm going to say close. The reason I'm going to say close is that the running time is the height of the tree. And hopefully that's log n, right? If it's not balanced, it might not be. But if you maintain more or less balanced, yeah. No, because you're just walking down a path. All right. So you can we're going to do running time later. If you want to look at all the nodes, that's order n. If you want to walk down a path in a binary tree, it should be log n. We're out of time. All right. Yes. Yeah, max it's n. But we're going to keep our tree balanced. So it will be log n. I was just messing with them. That's a whole lecture. You go like this. You rotate. We'll do it. Everybody good? Good luck with the assignment. What does it do? Monday, what time? Oh, midnight. Okay, good. So you'll see me again. Yeah, can I get out of here? No rush. Thanks for trying.
I didn't even know what to do.
No, somehow when I clicked there, said new, sometimes it would give me a box to open at York, and sometimes it wouldn't.
Yeah.
And then when I got the box, it wouldn't let me log in. And all right, what am I doing? Thanks so much. What are we doing? We're logging off of this.